Welcome to my study. We're going to talk today about Chapter 3 in the Geary book, which is about some famous episodes in the history of science. So it's a bit of review of some episodes, major episodes in the history of science that are fun to remind ourselves about. I think most of them you'll probably already be familiar with, but it's always fun to remind ourselves of some of the great episodes that have happened in the history of science. What we're going to do in discussing these particular episodes in the history of science is practice applying the Geary model to each of the episodes in question, filling in the chart and the diagram to characterize what happened in the experiments and the episodes that we're talking about. So let's take a look at the slides and think about how this is supposed to work for the Geary model. The episodes in the history of science that we're going to look at spread out over many of the sciences that you can study and learn about independently on their own. So we're going to look at examples from astronomy, physics, chemistry, biology, genetics, and geology. This is useful because if you have a decent model for how to understand scientific episodes, it shouldn't be, say, easy to apply them to physics cases, but harder to see how it's supposed to apply to genetics or geology. So one of the advantages of the Geary model is that it's topic independent. It's supposed to work no matter what scientific episodes we're looking at. In Chapter 4, when we get to Chapter 4, it should also help us see what goes wrong in cases of pseudoscience and marginal science. Let's remind ourselves of our primary vehicle for understanding things on the Geary model. Primarily what we're interested in are cases where we have contrastive situations. So we have two different attempts at understanding some phenomenon that we're interested in nature, and we construct a diagram. So first we have model number 1 with its predictions. We have the part of the real world that we're interested in understanding, and then we have a second model. From the real world, part of the real world that we're studying, we will glean some data, and so we need to know what model number 2 predicts as well. So those are the 6 fundamental elements: reality and the data that it produces, 2 models and each of their predictions. Once we gather the data, after figuring out what the predictions are and getting the experiments that we want to run finished, the question of fit arises between the models and reality. To get the predictions, as we've talked about before, involves a fair amount of calculations from the model to see what each of the models predicts. And then we run an experiment on the part of the real world we're interested in. We then check for agreement between the predictions of the first model and the predictions of the second model with respect to the data in question. And then we can draw conclusions for steps. I guess it would be steps 7, 8, and 9 on whether one of the theories is confirmed, one of the models is confirmed more than the other. So let's apply that model first to some astronomy. In particular, what we're interested in is the Galileo experiments. Galileo was one of the fans of the heliocentric conception of the solar system, and he was opposing the Ptolemists, who were geocentric theorists. So the geocentric theorists said that the Earth is at the center and everything else revolves around it, including the sun. Now, I found these different diagrams. Sometimes the diagrams have the sun inside the orbit of Mercury. I think that's the more natural one, but it doesn't matter whether inside or outside. I suppose there could be different geocentric pictures of the solar system, depending on what order you put things in. The planetary orbits were pretty constant between the two models. So Mercury is closer than Venus, Venus is closer than Mars, next out is Jupiter and Saturn. So the thing that has to move, of course, is Earth. It has to come in and either change positions with the sun or just be at the center with the sun next to it. So in any case, that's the two competing systems that we're looking at. Notice on this diagram, the Earth is at the center, immediately followed by the sun, with the other planets in orbit outside the range of the sun. So that's a different diagram than the previous slide. It's interesting to see that the geocentric theory gets presented in different ways. Presumably, there are different alternative theories applying the same geocentric model. In any case, Galileo thought, I can use the differences between these two approaches and do an experiment on Venus, the phases of Venus. So the phases are the shadows. So if you look at Venus at different times, if it's orbiting around the Earth at the center, then you're going to get the relationship between the Earth and the sun will be different. So you will get, depending on where Venus is in its orbit, different shadow patterns on the face of Venus. On the other hand, if both the Earth and Venus are revolving around the sun, the shadow patterns are going to look different. Blue is supposed to be the shadow. Yellow is supposed to be the lit up parts. So Galileo figured out that the Ptolemaic system should display different phases of Venus, and the Copernican system would display other phases, other shadow patterns. Now, what's interesting about this is the predictions were generated, but we didn't have any way of seeing Venus close enough up to see which one was the case. So Galileo just built a really fancy telescope to do the visuals and found out that the patterns fit, not surprisingly to us, the patterns fit the Copernican system. People weren't originally persuaded by this because they doubted the reliability of the machine, the telescope that Galileo had built. But after studying optics enough, they came to see Galileo did have a good instrument, and so the results came to be established. So how do we use this episode with the Geary model? Well, first, what we're trying to understand is something about the celestial bodies, in particular, the sun, the moon, and the planets, in how they relate to each other. So we have two models. We have the Copernican model and the Ptolemaic model. The Copernican model is heliocentric, the Ptolemaic model is geocentric. It turns out that the experiment generates no fit between the Ptolemaic system and the celestial bodies, but does generate fit between the other two. So that result is derived by various calculations, the predictions of the two models for different phases. Let the phases be the ones predicted by the Copernican theory. And so the Ptolemaic system says, nope, you're not going to see that prediction come to be. And then you run the experiment, you build the telescope, you get the data, and you find out there's agreement between the Copernican theory and the data that you acquire, but there's no agreement between the Ptolemaic model and the data that you've got. So that means in this comparative situation, the data that we have, at least we can say this much, confirms the Copernican theory over the Ptolemaic theory. Whether or not it confirms it decisively, or whether it decisively refutes the Ptolemaic system, we don't say anything at this point. That's a further point down the road in evaluating various experiments. But right now, all we're interested in is the comparative question of whether it confirms one more than the other. Our second example is going to be about Halley's Comet. So if you're inclined to pronounce it Halley's Comet, it's because you're confusing Halley, the historical figure, with Halley and the Comets, a nice 1950s, 1960s early rock group. So if we were in class, I'd pull up a YouTube video and play. Maybe it's Dance Around the Clock by Halley and the Comets, so you could get some feel for who Halley and the Comets are. But Halley's Comet is a comet named after Halley, who predicted its appearance. I believe the year is 1758, but I have that in the notes. So we'll see if I'm remembering correctly. First, a little bit of background about Newton's model of bodies, the 4 laws of motion, because these are the laws that Halley used to predict the return of this comet. So first, what are Newton's 4 laws? The first law is the law of inertia. If no force acts on a body, momentum is constant. The second is the dynamic law. If a force is acted on by a body, it accelerates by an amount directly proportional to the strength of the force and inversely proportional to its mass. In other words, force equals mass times acceleration. Geary, by the way, puts things in ordinary English because he's used to teaching people that had certain, maybe you call them phobias about mathematical formulas. Sometimes when you see a formula, there is a certain kind of person for whom that shuts down all understanding. Geary is trying to be sensitive to that, so he's trying to formulate these laws without reliance on any mathematical notation at all. I'm actually the other kind of person. I find talk about direct proportionality and inverse proportionality to be harder to understand than the simple mathematical formula. And notice what Geary does is, instead of giving the formulation in terms of what force is to be identified with, he actually does it in terms of acceleration. Acceleration equals what? Force over mass. Now, I prefer simple mathematical formulas, and maybe some of you do too, but in any case, if you prefer ordinary English, that's what he's trying to do to help you. The third law is the reciprocal actions law. The forces exerted by 2 bodies on each other are equal in force and opposite in direction. There's an interesting and little noticed fact about this law. Notice that this law applies to every body, every piece of mass throughout the entire universe. Every piece of mass throughout the entire universe exerts some kind of force on every other body throughout the entire universe. There's no separation of space or time that gets you out of that implication of this theory. Finally, any 2 bodies exert attractive forces on each other that are directly proportional, excuse the typo, to the product of their masses and inversely proportional to the square of the distance between them. So force equals, where G is a gravitational constant, the gravitational constant, whatever that is, times the product of the masses divided by the distance between them squared. That's the particular force, measure of the force exerted between any 2 objects whatsoever. So the key terminology in the Newtonian model of bodies is this. You have the notion of position of an object, velocity, which is change in position per unit of time, acceleration, which is change in velocity per unit of time. You have mass, which Newton described as quantity of matter. You have momentum, which is mass times velocity. And you have force. Force is whatever makes for change in motion. So notice many of these terms are defined in terms of the others. So position is basic, and velocity and acceleration are going to be defined in terms of it. Mass is also basic, and momentum is defined in terms of it, as is force. So what's new in the Newtonian picture, and what is distinctive about it? Well, Newton's laws unified the theories of celestial and terrestrial motion. So lots of stuff was known about the motion of bodies in the heavens, and other things were known about the motion of things on the earth, but there was no unified theory of the two. And one of the central aspects of advancement in science is unification. If you can unify various systems under a common framework, that's a wonderful accomplishment. And that's what Newton is primarily noted for, unifying theories of celestial and terrestrial motion. What's new in the theory itself here can be characterized in terms of what needs explanation. The old physics was derived from Aristotle. So Aristotle, remember, lives in the 4th century BCE. Aristotle, famous student of Plato's, and maybe in terms of world history, more famous as the most famous teacher of Alexander the Great. And remember, Alexander the Great dies in 323 BCE. So Aristotle's in the 4th century BCE. And notice it's a long period of time from there to Newton in the 16th century. So we get roughly 2,000 years where Aristotelian ideas dominated physics. For Aristotle, the fundamental problematic had to do with moving, with motion. What requires explanation is when an object moves. If you're just sitting there doing nothing at all, you're at rest, and that requires, for Aristotle, no explanation at all. What requires explanation is you stand up and you leave the room. So you began to move. That's what we need to explain. If things are just sitting there doing nothing, there's nothing to explain for Aristotle. For Newton, that's not correct. The natural state of an object is inertial. So what needs explanation is changes from the inertial state. And notice, the inertial state could be one of being at rest, but also one of moving at a constant speed. So for Aristotle, force is what moves an object from being at rest to being in motion. For Newton, force is what causes change in motion. Now, the differences here are very subtle, but they're important ones. And it presents an entirely different problematic when you're looking at change in motion rather than motion itself as being the thing to be explained. So, as an example of using Newtonian theory, think about the orbits of the planets and the comets that show up that Halley knew about. Now, Halley dies in 1742. He publishes his predictions about this comet in 1705. And the prediction was that the comet would return in 1758. So he knew about a comet experience from 1531, from 1607, and from 1682. Now notice the time frame differences here are about 75 years. So if you know about 3 comets that are similarly described, and they showed up 75 years apart, you might suspect that it's actually a reappearance of the same comet, which is what Halley surmised. He surmises that it's the same comet since the orbits were nearly identical. And so what he did was he started calculating. He calculated that the comet would return in 1758. Now, if you just did simple subtraction, you'd get a 76-year gap there, a 75-year gap to the next one, and then his prediction is a 76-year gap again for the next one. But what's unique here is that he used Newton's laws, common knowledge about the size of the planets and the nature of their orbits, and published this prediction in 1705. Unfortunately, he died in 1742, so he didn't get to see his prediction come true. But in fact, the comet did return in 1758. So how are we supposed to understand this one? Well, the thing we're trying to understand is the path of a comet or a group of comets. For contrastive situations, we're supposed to have two different models, but it's not clear what model is being opposed to Halley's Newtonian model. So we'll just put question marks there. Since we don't know what the model is, we don't know whether it fits or doesn't fit with the path, but we do know that the Newtonian model fits. So we do some calculations. We can't do much in the way of predicting from an unknown model, so we just put question marks there. But for the Newtonian model, we can calculate and get a prediction of 1758, which is what Halley did. And then you wait around. Halley had to wait too long. He died 16 years before he was able to run the experiment, but other people ran it for him, and it turned out the comet appeared in 1758 as predicted. So there's agreement between the prediction of the Newtonian model and the appearance of the comet, which is the data from the experiment that you're running. We just have question marks all over the place when we're trying to talk about what an alternative model would look like. But in any case, we don't have enough information over here. So all you can say is, I guess we'll have to go back to the non-contrastive confirmation situation. And you ask yourself, was this agreement to be expected or not? That's a hard question to answer in this case, but at least we know that there's some degree of confirmation for the Newtonian model generated by the path prediction for Halley's Comet. Maybe it's not super strong, but it's present. The problem is we already knew from past historical records that a comet like that to be predicted by Halley had been showing up every 75 or 76 years. So maybe you'll say, just given our background knowledge, we had some reasonable expectation that another comet of the same sort was going to appear around 1758. Notice, however, that our data didn't actually, our prediction from past pattern didn't tell us 1758 rather than, say, 1757, whereas Halley's prediction using Newtonian theory was much more specific. Okay, let's move on to chemistry. The chemistry that we're going to look at is a really famous, wonderful experiment by Lavoisier. Lavoisier is the person who developed the oxygen theory of combustion. So the oxygen theory of combustion says the reason things burn is because of the presence of oxygen. Prior to Lavoisier's work, the standardly accepted theory was the phlogiston theory, that combustion was due to the presence of phlogiston. Now, in one sense, the phlogiston theory was not an informative theory in any way at all. Phlogiston was originally claimed to be the stuff that gets released when things burn. So you build a campfire, you're out camping, you build a campfire, you throw some logs on it, and pretty soon there's much less material there than was there at the beginning. So the idea was, when things burn, something gets released. Let's call that phlogiston. It was just a description of the stuff that gets released. Gradually, it came to be a theoretical entity of a certain sort, because you can't really see the stuff that's being released. You see smoke, you see sparks going up, but you're not seeing phlogiston, it doesn't look like. In any case, Lavoisier wanted to test the phlogiston theory, and he did it with the following apparatus. The hard thing about combustion is it's hard to control. So here's what Lavoisier set up. So down here we have a bunch of water, and then we put up here mercury. And we're going to get the mercury to burn by using a magnifying lens to focus sunlight. And then we're going to control the amount of air available for combustion by putting a domed lid over the whole thing. Now, basically, what's going to happen, calx is the burned remnants of the mercury. So the prediction of phlogiston theory is that after burning, the weight of what's left should be smaller than what we started with, because something's going to get released. And when something gets released, it will be released into the atmosphere, but it can't get out because there's a domed lid that's submerged in the water. So what we should expect is more stuff in here, which will either push the dome slightly up or depress the water level, maybe both. So it's a very nice experiment calculating the predictions of phlogiston theory. Now, at this point, the experiment is not designed to show that oxygen theory does a better job of explaining it. That came later. This experiment predates Lavoisier's development of oxygen theory, but we're going to use oxygen theory as the alternative to phlogiston theory here. So we're trying to understand combustion, and we have two models, that combustion is due to the presence of phlogiston, or combustion is due to the presence of oxygen. What we're going to find is that the oxygen theory fits with the combustion that occurs, and phlogiston theory does not fit. The reason is, going back to our diagram, the water level, the really instructive thing is that the water level rose because of combustion. Why would that be the case? Well, obviously, whatever is up here in the atmosphere, some of it got consumed as combustion occurred. That generated a force that raised the water. So phlogiston theory in particular predicts water level will go down. Oxygen theory predicts water level will rise. That's the distinctive result of the experiment. There's also the weight question. So the oxygen theory proposes that the calx that's left will weigh more and that the water level will rise. Phlogiston theory predicts the opposite. That makes this a really nice, crucial experiment between two models, because you get contrary predictions from the two. That will make the experiment be singularly determinative here. And what we find is the weight increases and the water goes up as well. So there's agreement between the oxygen theory and our data, the prediction of the oxygen theory, and disagreement between the prediction of phlogiston theory and the results of the experiment. Very nice, important experiment in the history of chemistry. And to my mind, one of the really interesting features about it is the ingenuity in setting up the experiment itself that Lavoisier showed. You have to control combustion, and you have to isolate the results of the combustion using the water bath and the glass dome over the top of it. That's really ingenious. Biology, we're going to look at some Darwin stuff. So here again, we don't have much of an alternative theory to Darwin's evolutionary theory, but it's about the beaks of finches. So notice finch beaks come in a wide variety of shapes and sizes. Some are shorter and blunter, some are longer. This one especially is very thin, and this one is super thick. And it turns out the kind of beak you have determines the kinds of things you're able to eat. So that's one of the things that Darwin observed, and he wanted to know, I wonder why finches have such a variety of beaks. So finch beaks are something you're trying to understand, and you need two different models. So he had a model, natural selection, and maybe we should just talk about special creation as an alternative model. It's not clear to me that special creation is a suitably scientific model, but it's hard to say what makes something be a scientific model versus, say, a religious model, but let's just go with special creation being a scientific model. So we have two models, and there's no special fit between special creation and the variety of finch beaks that we get, but there is fit when you look at what natural selection predicts. So calculate. What does special creation predict? I'll let you think about that and then calculate what does natural selection predict. Now, special creation, does it predict that there'll be no variation among finch beaks? That's very hard to say. Who knows what special creation is supposed to predict? It's very hard to get any particular predictions from special creation. What you get instead are post hoc appeals to the mind of God or the mind of a designer. So after you see what the world is like, then you say, here's what the designer must have been thinking. Maybe that's how the calculations go, and that's disappointing because you want a theory well developed enough to be able to actually do predictions, rather than just once you see the results, then you invent a story as to why those results are the product of your favored theory. I'll tell you a really interesting story about my kids. When they were little, this has to do with special creation. When they were little, we took them to Branson and went to the IMAX and watched a thing about deep sea life, which at the time they found fascinating. I think my son was about, probably 12 and my daughter 7 at the time. So we're sitting in an IMAX listening to this thing. And as is typical of these documentaries, lots of the features of creatures that are noted are explained in terms of natural selection. But they got to one creature, and apparently there's no natural selection story currently known at the time of the creation of the movie for why the feature was present. So the person doing the documentary says in the documentary, we don't know, we don't understand why this fish or sea animal of whatever variety it was, we don't know why it has the feature that it does. And somebody booms out with a really loud voice at the back of the room, it's God. Well, this is Southern Missouri, it's Branson, it's heart of the Bible Belt. It's not surprising that somebody would think that. But think about the quality of the explanation that you get. So presumably it's a kind of special creation of this feature. But you can't predict based on the fact, suppose it's true that God had a special design in mind and created that sea creature with a particular feature that it had. You couldn't have predicted that. So the theory is amorphous and vague enough to be compatible with whatever feature this creature had. But you can't look at the theory and do any sort of calculation that will tell you what to expect. With natural selection, there is a calculation that's possible. So you do the calculations, and based on natural selection, you should find some sort of adaptation occurring. Then you run your experiment, and you notice that there are, in fact, beak changes, whereas perhaps no such variation was to be expected based on special creation. After all, why should such adaptation occur in the structure of the beaks? There's no particular reason to expect that, so you can't calculate some expected variation. You can, however, do that from natural selection because it's supposed to put pressure on things to adapt or die. So you get agreement between the prediction of the natural selection theory, but you don't get agreement between the prediction of the alternative account. Fifth example from genetics. So here we're going to talk about Mendelian genetics. Mendelian genetics, by the way, some of his data is almost certainly forged, faked, because it fits what statisticians call data that's too good to be true. But here's a quick diagram of a pattern that Mendel noted. If you've got dominant and recessive, so you start out with seeds that are being produced, and some of them are yellow and some of them are green. And if yellow is dominant, then in the first generation, the ones that propagate completely yellow ones, you take samples from that, and those that propagate completely green ones. This is the first generation, the first parents that you're going to use. And what you notice in the second generation is all dominant. So all of the seeds in the second generation are yellow, but then in every successive generation, it turns out you get a 3-to-1 ratio of yellow to green, and that continues into the future. So that's a quick chart about the yellow and green ones. The more interesting experiment is the one that you probably learned in high school biology. This is about tall and short, I believe it was pea plants. So what you should expect is if tall is dominant, then in the second generation, you'll get all tall, and then after that, you'll get a 3-to-1 ratio of tall to short. The alternative model is the blending model. The blending model is something like the kind of model we apply to, say, the height of children of human beings. There's supposed to be a formula, by the way. So if your child is a boy rather than a girl, you take dad's height, if it's a boy, dad's height plus mom's height plus 5, and divide by 2, and that gets you the boy. And if you're going to predict the girl's height, you're supposed to do dad's height minus 5 plus mom's height divided by 2. At least that's what our pediatrician told us. That's a kind of blending model. The most straightforward blending model would just average the two heights. Turns out that blending model for kids doesn't work because height is gender correlated. Okay, in any case, the blending model for the peas should predict if you cross a tall and a short, you should get a medium, and you should get mediums from then on. Okay, so now we have two models, and we can construct our diagram. We're looking for inherited characteristic traits. We've got the two-factor recessive and dominant that Mendel was proposing. The alternative is the blending model, and after the experiment, we find fit with the two-factor model, no fit with the blending model. So first you have to calculate, and the picture earlier shows the results of the calculation. You should expect medium offspring from the blended model, and at least 2 generations out and beyond, you'll expect a 3-to-1 ratio from the two-factor model. So you do your test, and you gather data. Now it's here where Mendel is accused of fudging the data, because you shouldn't expect absolutely perfect 3-to-1 ratio results. The world is a messy place, so you should expect run the experiment multiple times, and you should expect results that sort of vary in small ways around this 3-to-1 ratio. But his data was just too good to be true. Sad day for scientific honesty, but you can run the experiments without fudging the data, and you'll get what the two-factor theory predicts. So you get agreement between the data and the prediction of the two-factor theory. You don't between the data and the prediction of the blended model. So you get some degree of confirmation, contrastive confirmation for the two-factor model over the blend model. The last case we'll talk about is a case from geology. This concerns the behavior of the seafloor and the presence of volcanoes and different visible land masses on Earth. So prior to the 1960s, I think the 1960s is when I first heard about plate tectonics in school, and I found it astonishing that continents used to be together and had drifted apart. So prior to the development of plate tectonics, contractionism was the standard model for what we observe. And the example that I was taught was, think of what happens when a grape turns into a raisin. So you think of the Earth as being fundamentally molten, and then it cools. And as it cools, it hardens because moisture is lost. That's what happens when you dry a grape and it turns into a raisin. Now, what happens when that occurs is the cooling object gets smaller and its surface gets bumpy. So raisins have, okay, I don't pretend to be an artist. Raisins have a very bumpy surface with certain parts of it elevated and other parts depressed. The grape you started with didn't look like that. It had a smooth oval kind of shape to it. But what you should expect as the Earth cools is this contractionist phenomenon where some parts are higher and some parts are lower. So some parts will still be underwater and some parts will be above water. Now, what's interesting is new data was developed which suggested that that was wrong, that really the explanation for the land masses wasn't that they survived retrenchment as the seafloor was sinking, but rather the seafloor was spreading and driving molten stuff up, which was creating volcanoes and mountain structures from that. So how did that come to be seen as better fitting certain data? Well, here's what we know. The magnetic poles switch valence at the poles of the Earth across time. That's what we know. We've known that lots of times. And if you look at the vertical layers for the land masses, you can find these polarity shifts at various times. That was known already. The new data was you send ships across the ocean, and they're figuring out whether there are similar polarity shifts at the bottom of the sea that are at the vertical level. And stunningly, the polarity shifts are found there. So at the vertical level, the polarity shifts match what we already knew about the vertical. Sorry, I mixed that up. This is horizontal, not vertical. This is vertical, not horizontal. So what we found is a match between the vertical polarity shifts already known about and the horizontal polarity shifts discovered by data drawn from ships that were trying to detect that. It's a really fancy, it's really hard to gather this data, but it led to the idea that the mountain ranges, the elevated land masses, didn't just survive the shrinking of everything else around them, but were really caused by magma coming up from the ocean floor and then going vertical. And that would explain why the polarity shifts can be noted. This is in millions of years. The polarity shifts don't happen really fast or frequently, but they do occur. Okay, so here we have land and sea heights and masses. That's what we're trying to understand. You have a contractionist model. You have a mobilist model, which plate tectonics is a particular instance of. And what you see is that there's no particular fit based on the particular data that we're going to use between the contractionist model and the real world. And we do have fit from a certain mobilist model and the phenomenon we're studying. So we do calculations. And contractionists don't predict any particular correlation between the polarity shifts at the vertical and horizontal levels. It's not that they predict that there won't be a correlation. It just has nothing to say about it. So there's no prediction of data from that model regarding the phenomenon being studied. But there is from the mobilist model. So the magnetic data, magnetic correlations are what we should see between the horizontal and vertical levels. So now we gather the data, which was a massively expensive task, but a really important one for understanding land masses and their relation to the seas. And so what you get is an agreement between the data and the mobilist model predictions. And you get no agreement between what the contractionist model predicts because it doesn't predict anything. So that's the end of our discussion of these great episodes across many different scientific disciplines. So these are great episodes in the history of, let's call it, respectable science. In Chapter 4, we'll turn to some more ignominious episodes in the history of marginal science.